Thank you very much, Lavi. So it's a great honor to be here today. There's a great research vibe around here. Okay, so I'm Alex Ilgayev, and today's topic will be breaking open source CI/CD pipelines using code search and injection. So let's start with the agenda. Before digging into vulnerabilities and exploitations, first we'll want to understand what is CI/CD, what is GitHub, what is GitHub Actions, and I will try to explain why it's such a powerful also build system. Then we'll try to understand what kind of misconfiguration GitHub Actions workflows could have and how can we exploit them, what consequences we can reach by this exploitation. And finally, we'll go over some of the possible mitigation to stop such attacks. So I'm Alex Ilgayev. I'm a senior security researcher at Cycode. Previously, I also led the malware research team at Checkpoint, where I gained a vast research experience in reversing complex pieces of malware. And nowadays at Cycode, I research software supply chain security vulnerabilities and try to find mitigations for these vulnerabilities. So for most of its history, GitHub was all about storing source code. Since 2018, it went into different but a similar direction by announcing GitHub Actions, a CI/CD platform to automate development workflows. And since then, it became extremely popular. It has over 12,000 custom actions. It has millions of public workflows. Almost every possible ecosystem and environment has some support in GitHub Action. It becomes a really great platform. So what is CI/CD and what could you do with these actions? So the most simple thing you could do, just take your code, download, compile it, package it to some maybe container image, and push it to your chosen Artifactory or artifact registry. It could be Docker Hub, JFrog, Nexus, or whatever you want. And additional workflows you could do with GitHub Actions, like creating schedules, vulnerability scanning for your code. You could create some tests for a fault pull request. You could do some labeling to help the maintainers triaging the issues in the project. And you could do like whatever workflow you would choose. So how GitHub Action looks like? It has three parts. It is first it's a YAML file. It has a name. In this example, it's GitHub Actions demo. It has a trigger, which instructs the GitHub Actions service when to run this workflow. In this example, we have a trigger that's called push. This means that on every push to the repository, GitHub Action will run this workflow. And finally, it has several jobs. In this example, we have one job that has a single steps that echoes hello world. So I am, as a developer, taking this file, putting in some designated path in my GitHub repository, in that GitHub/workflows path. And that's it. GitHub will schedule this workflow whenever I push a new code to the repository. It's extremely simple. So before we dig into the vulnerabilities, we need to understand some core mechanics of GitHub Actions and how it works. So one of the core mechanics is the GitHub Runner. The runner is the entity that runs the actual actions. It fetches the jobs from some API server, and it runs them, executes them. So this runner could be run either on a GitHub hosted machine, which is the popular method for open source projects, or it could be run on some self-hosted machine, which is popular among enterprises. So in addition, when you run this on the GitHub hosted machine, it also runs as an ephemeral environment. This means that every job will be run on a clean VM, and whenever a job is over, the VM will be deleted completely. So in addition, for each such a run, it also receives a temporary GitHub token, which we'll elaborate soon. So what is the GitHub token? The most standard method for accessing GitHub API for most of its existence was through personal access token, which is bound to the user identity and the user permissions. So this has several drawbacks. The first, it's very permissive. You can't really limit it to certain repositories. And second, it has a really long lifetime, which is a problem if that token leaks. So GitHub came with an idea for creating a GitHub token, which will have a read-write permission for most of the events for that specific repository where you define your workflow. In addition, it also limited to the action execution period and with 24 hours at most. And it is the preferred method by GitHub to be used with all the custom external action used in your workflow. So additional important mechanism in GitHub Actions is secrets. To create a meaningful workflows, you need to be accessing some sensitive assets. Could be your cloud environment, could be your package manager, it could be other repositories, it could be GitLab, Bitbucket, or etc. So to implement this, you need to define some tokens and assets for your workflows. You can define this with three manners. The first, it can be defined on the organization level. Then it will be exposed to all the repositories in your GitHub organization. Or you could be defined on the repository level. Or finally, it could be defined as a repository environment, which will be talking at the end in the mitigation part. So now that we understand what is GitHub, what is a GitHub action, why it's so powerful, let's understand what kind of vulnerabilities we can have in GitHub Actions. So we created some simple workflow. That's called issue check. It will be run whenever a new issue is created on GitHub. Issue is a popular method to report about bugs or feature requests in the repository you're maintaining. So this workflow will be, whenever a new issue is created, will be running this short bash script that checks what is the issue title. So you can maybe notice there's additional syntax here in the workflow, this double curly brackets, which is an additional method for workflow developers to receive inputs from the GitHub Actions service. It could be some environment variables, or it could be the input that received from the user. In this example, if you create a new issue, you want to receive the issue title and body, the one who created it, and more. So this script checks if the issue title contains the word bug. If it contains the word bug, so we call the GitHub API with a GitHub token, and we add a new label to the issue with the word bug. This could potentially help maintainers to triage the issue in the repository. So on the first side, this workflow looks innocent, but it has a really big problem. This title isn't being sanitized correctly in that script. The GitHub Action Server just replaces the input with the value I give them, and potentially anyone could put some title that could contain malicious script. For example, if we have this title that we are finishing with the quotes and making a true statement in the if, later we're going to put everything we want. For example, I put sudo apt install figlet, which is a tool that helps you to print with pretty psychotext, pretty ASCII text, this psychot. So I managed actually to execute code on the runner from external input due to sanitization of the input. When I first did this, I was like, wow, this is cool. What could be the possibility of this? So at first, this is a bug, like what's going on? And then I went to the GitHub Actions documentation in the best practices, and understand it's not a bug, it's by design. And they're saying that when you're creating workflows, you should always consider whether your code must execute untrusted input from the attackers. Okay, this is interesting, but there's a chance that many open source projects, or many projects in general, do not know these best practices and may be vulnerable or exposed. So I thought what we could do with this. Luckily, there's an interesting cool tool GitHub released lately that's called GitHub Code Search. If I'm not mistaken, it's already integrated to the github.com lately. And it's a really powerful tool. You could search many snippets of code and put some parameters, and it's really interesting. So I put several snippets that identifies this vulnerability. And the results were tremendous. I found hundreds of interesting repositories and projects that were vulnerable to such injection attack. Some of these projects were extremely popular. I found this Liquibase, which is an extremely popular tool to handle database schema changes. I found this Dynamo, which is a project that's sponsored by Autodesk, which is a visual programming tool. There was a Fauna, which is transactional database, Wire, which is open source communication tool, Astro, which is static site builder, and more and more. This project has thousands of stars in GitHub and millions of users. Liquibase on its own claims on its site it has more than 75 million downloads. So we can safely claim that these vulnerabilities could reach millions of potential victims. Of course, that I disclosed this vulnerability to each and every vulnerable project, and they fixed it almost immediately. So you can ask yourself, like, what's the big fuss about it? I mean, you managed to execute code on some temporal runner, probably don't have any interesting assets in it. What could be the consequences of such code execution? So the consequences can be quite bad, and I'll explain. The first, you have access to sensitive assets within the workflow. There could be cloud tokens. There could be tokens for repositories, tokens for package manager, Docker Hub, JFrog, Nexus, ECR, GCR, you name it. And the second big consequence is that you have the ability to use the GitHub token, which I talked previously, to commit a new code to the repository, which could introduce potential backdoor and maybe create the next SolarWinds. Additional smaller risk will be the ability to run crypto miners and botnets on the runner infrastructure. So to explore these consequences, to show how it's possible to execute them, we created an additional vulnerable workflow which will follow us through the example. So we created a workflow similar to the previous one that is executed whenever a new issue is created. It defines a GitHub token as an environment variable and contains 3 steps. The first step will download the code. It's running checkout, which is an external GitHub action command. The second one is just echoes the issue title and description. And the third one will be running this short script to update the issue label with a new predefined label. So as you've seen previously, the second step is susceptible to code injection, just as in the previous example, because the input wasn't sanitized properly. So it's important to mention that the attacker has managed to get code execution at this specific point in the second step. So to explore, to understand the runner internals and to how can we leverage this code execution into our maldoing, we wanted to create a reverse shell from within the runner. How do we do it? We use a popular tool called ngrok, which is a popular tool for doing TCP and HTTP tunneling. We just run ngrok for some port from our own computer, received some endpoint from the ngrok cloud, which we'll be using later to do a bash reverse shell. And we send this ngrok endpoint to the malicious input to the issue. So let's look at it. So for our previous example, if we will create this issue title with the bash reverse shell after we created the ngrok endpoint, we will get a reverse shell from inside the runner to our own computer. We use this reverse shell to explore the runner internals to understand why can we do that. So let's go back to the example. So the first thing the attacker could do, which is the most simple, take all the environment variables and to exfiltrate them. Inside these variables, we have the GitHub token, which is a privileged token to access to the repository, and the attacker could use it maliciously. The second was to leverage that we use the checkout command. Behind the scene, to this checkout command, we're also sending a default parameter. One of the default parameters is the GitHub token, which we previously told you about. So an additional interesting fact is that whenever you use a token to clone a repository, it also saved as a configuration parameter. So as an attacker, I could fetch this .git/config file after doing this checkout command. I would find this authorization line, I would pipe it through base64 decoding, and I will get the GitHub token. And the third method is a bit more complex. During the runner experiments, we understood that every script, every shell script is being written to the disk before executed. So we have two scripts in our example, and these both scripts were written to the specific directory, and they were written after the GitHub Actions replaced the secrets in the script. So if we get a hold on this script as an attacker, well, maybe we could fetch the tokens from these scripts. Unfortunately, we had code execution privileges only in the second step, and we don't see the third step yet because it's fetched from the GitHub Actions service only when it should be executed. But we could easily put some persistent script on the machine, on the runner, and whenever the third step will be executed, we'll send it immediately to our control server. So we're just creating some simple server that records all the requests. We created some script that monitors changes in that specific directory. Whenever it finds one, it sends it immediately to our server, and we run it as a simple Docker image on the machine. We'll see it soon in the demo. So we have several demos to demonstrate what is the capability of doing for these consequences of these vulnerabilities. So for the first demo, we'll show how we're able to exfiltrate in this simple example both the GitHub token and the token in the third method. So as you can see in the demo, first we're on the left side, we're setting our server to record all the requests. On the right side, we're sending the malicious input to the repository. This input will exfiltrate secrets in several steps. The first step will send the GitHub token, which you fetch it from the environment variable, which you could see it right now. And for the second step, we're putting that persistent script to monitor all the shell files and to send it whenever it's created. You can see what we received, not only the token, we received the entire script containing the token inside of it. So the second demo will show how we are able to commit code into the repository. For that, we created some script on the left side, which contains simple Git commands, nothing fancy there. And the right side will show how we're going to fetch that script and run it inside the runner. So let's see that in action. You can see we have a simple repository contains a directory and a file. So we are creating a new issue for that directory. The title contains several commands in the injection. First, we're fetching the script that should commit to the repository. We're giving it proper permissions. And then we're running it with the file we want to commit with the path where the commit should go in the repository. So now we will go back to the repository. We can see we have an additional file that committed due to the injection. And in addition, you could see that the commit was made by someone's called maintainer name, and the commit message was innocent commit message. So we have the ability also to forge commits and to hide our tracks. And the third method is thank you very much. The third method is a bit more complex. Up to this point, we show how we are able to exfiltrate secrets that were used in our specific workflow. But there's many additional secrets in that repository. There's additional workflows that using maybe other secrets. How can we get them as an attacker? But we also show that we can commit code. So let's commit a new workflow that try to exfiltrate all the secrets of the repository, not only specific ones that we were using in the workflow. So how can we do that? We created a new workflow on the left side that has several parts. it will be triggered whenever the vulnerable workflow is over. And it will write all the secrets into some JSON file, it's called .secrets, and we'll send it to our server. And in addition, the second step, we also want to delete that workflow to hide our tracks. So the maintainer wouldn't know that we done anything there. So on the right side, this is the API that we use to commit that file into the repository. It's different than the standard Git commit procedures, but it contains the file as a base64 encoded, and it also contains the precise location where we want to commit this. So let's see this, the demo. First, on the right side, we are setting our server. And now, we are creating a new issue. This time we're creating as in the body and not in the title, because the title limits the number of possible characters that we can insert. And the issue body is so long because it also contains the entire workflow encoded in base64, which is one of the parameters for the API call to GitHub. Let's wait a few more seconds. Behind the scenes, it creates a new workflow. Here it goes. So we received on our server both secret 1 and secret 2, which is actually organization secrets. They weren't defined in the repository at all. We have the previous bot token and GitHub token secrets, which actually got everything exposed to that specific repository. So that's it for the demos. Thank you. Okay, let's see how can we mitigate this. So first, avoiding run steps. This is not always possible, but when possible, it's recommended. For example, instead of invoking GitHub API into update labels, we can use external action that does precisely the same. Because these actions are usually developed in Node.js, which is more securely designed than running some bash scripts. The second most effective method is sanitizing your input. Instead of using this issue title or description inside your bash script, just define this as an intermediate environment variable and use that environment variable inside your script. Even if this variable contains code, it will be treated as text only. The third method will be to limit token permissions. This is an extremely effective method for post-exploitation because it will deny not only this such injection attack, it will deny any possible attack on the workflow. So even if the attacker managed to RC into your build server and to run code, he won't be able to use the GitHub token maliciously because he won't have the permission to do that. Another method is to limit secret exposure. You can, if you define organization secrets in your GitHub organization, you can limit what repositories they have access to. So you could limit the post-exploitation possible by the attacker. And finally, there's an additional feature in GitHub Enterprise, relatively new, that's called environments and environment secrets. Environments could be staging, production, test, etc. And these environments could contain secrets and be protected by proper branch protection. So it's quite an effective method. Okay, so let's see what we learned from this talk. First, even when GitHub does many of the security for you, it creates your thermal environments, VM isolation, I wanted to show you that your build pipeline still can be compromised. As we've seen in the GitHub Actions documents, in the best practices, GitHub delegates many of the security to the developers. And I was a developer myself. I know developers make mistakes, and it should be handled carefully. The third, as we showed, the consequences for such build compromise can be quite disastrous. It could be exfiltrating your sensitive tokens. It could be allowing attackers to create backdoors in your repository, which will be deployed to end users, and more. And finally, securing your pipeline is a matter of faith. GitHub provides you a handful of solutions and mitigations to protect your pipeline accordingly, so you should use them. Okay, so thank you very much. Thank you to the great conference for inviting me here. You're welcome to check the full blog, full details in our recycled blog, and you're welcome to approach me with questions whenever you want, even now. Thank you.